Hello, class. So on this video, we're going to be talking about forced motion. Right? In the two previous examples, we're assuming that there were no forces requiring or forcing an oscillation pattern on the system. Right? The motion of the system was entirely dependent by the restoration force and by the weight of the object. And of course, if there was damping, that energy would be lost, but we're not forcing any oscillations on the system. Right? So what happens if we do force oscillations on the system? Well, let's go back to the drawing board and let's go back to, not all the way back, but down to Newton's second law, right? When we know that the mass times acceleration, so m times x double prime, equals the sum of all the forces, right? Which we have negative kx, right? Because of the restoration force of the spring. We have minus beta x prime, right? This coming from damping. And now we're going to add another force. Right? And this f of t is going to be the forcing, or the force that is forcing oscillations on the system. Now, I write it as plus f of t. You can think of it in a couple different ways. Whichever way you choose is up to you. You can think of it as being positive because this force is actually going in the direction of motion. Why? Because it's actually forcing the motion. You can think of it that way. Another thing you can think of it is that, and that's the best way to think of it. But another way you can think of it is, well, the sign is just going to be determined later. But I think the best way to think of it is this force is going in the direction of motion, so it's going to be a positive force. And again, remember, we had minus beta x, right? So it was the beta x prime was negative because this is a force going opposite the direction of motion, right? So that's the best way you want to think of why the signs are like this. These two forces here are going in the direction opposite to motion, and this is going in the direction of motion. So we can just go ahead and rewrite our differential equation, right? Add everything to one side, except for f of t, we're going to leave by itself here, and then divide by m. And what do we get? We get x double prime plus beta over m x prime plus k over m x equals f of t over m. Right? Remember, we can divide by m because m is the mass, which is non-negative. Right? So you can write it like this, and I'm going to write it how they do it in the book. So remember, this was 2 lambda. Beta over m was 2 lambda. So 2 lambda x prime plus w was the square root of k over m, so w squared is k over mx equals, and I'm just going to call this big f of t. So what's going on? When you add a force into this system, what happens is that you go from a homogeneous system, in the case when you don't have driving forces, to a non-homogeneous system, in the case that you do have a driving force. So this force here, remember this f of t is a force, this is forcing oscillations on your system. And that's, in terms of the setup, that's the only difference. So if we were to try to find or want to find the general solution without worrying about initial conditions as of right now. But if we wanted to find the general solution for this, we would have to do either method of undetermined coefficients or variation of parameters. Those are the two methods that we have for non-homogeneous systems. So if f of t is a combination of cosine, sine, exponentials, and polynomials, we can use method of undetermined coefficients. If it's not, then we have to use variation of parameters. Now, you can interpret this, or I could ask you to interpret what is going on. I could ask you to find a solution and interpret the solution. I could ask you to just look at this and interpret what's happening, right? So whenever you see something that's non-homogeneous, so let me give you an example. Let's say we have a system that looks like this. So x double prime plus 10x prime, so I'm going to try to copy the previous example, plus 16x equals, let's say we have cosine of 3x, and we have a 4 outside. Oh, t T is the independent variable, sorry. I could give you a problem like this and ask you to interpret what is happening in this system. Specifically, I could ask you what's happening here. Right? What is this doing to our system? You can see that this 4 cosine of 3t is a function, cosine of 3t, that's oscillating, right? It's oscillating with some period, the period being 2 pi over 3. Okay, so this thing here has period equal to 2 pi over 3. And amplitude, remember amplitude is the distance from the equilibrium to the highest peak of a mountain or the lowest bottom of a valley. Here the amplitude is given by force, whatever's in front of the cosine. Right? So you could interpret this by saying that we have a spring mass system with some damping, right? And then some, and then a restoration force acting as well from the spring. Then you could say, but, and even though we get solutions from that, but we're forcing oscillations that have a period of 2 pi over 3 and an amplitude of 4 into the solution, right? Or into the system. And then, of course, if we're forcing it into the system, we're forcing it into the solution, right? So you can go ahead and find the solution to this, see what the solution looks like, and see how this forced motion here affects the solutions. So I'll ask you to do something like this in the homework, and I'll ask you to interpret, what's going on, right? Because again, when there is a context to anything like this, and in this case it's a spring mass system, it's important for you to interpret what's going on in the system, what's going on with the solutions. But other than that, that's the only difference, right? The only difference in terms of solving the ODE is that we go from a homogeneous to a non-homogeneous. Okay. So again, I'll let you work on examples like this in the homework in the next one. Right? So for now, this is going to be all I'm going to say about section 3.7. Right? We spent a couple of videos on this section, but again, because it's important. Not only is I think the most important application that we're going to see, when I introduced it, I mentioned how it has applications to a wide array of almost every applied math area. And as I mentioned, this can be generalized if we let go of the assumption of simple harmonic motion. So if we assume that there's no restoration force on the spring, we can generalize this to more general sort of motion, which is called periodic motion. Right? But again, you'll see that in more advanced courses. Right? Okay. So this is it on section 3.7. We're going to start on chapter 4. Right? We already did part of chapter 4 and when we did section 3.2. And you'll see that the things that we're going to cover in chapter 4, they're basically not going to be new. It's all going to be already what we've covered, right, in section 3.2 and 4.1. The only thing is that we're going to generalize it to higher order ODEs. Right? So we did a lot of things for second order ODEs in sections 3.2/4.1. We're going to see what happens when we have higher order ODEs. But basically everything generalizes. There's nothing new to learn. Okay, so in terms of the difficulty, chapter 4 is going to be very easy because we've already learned everything there is to learn.